Alright, I want to do a quick drive-by on everything you've learned in this unit. So, starting with 4.1 through 4.2, we learned about radii and chords. You know what a radius is, you know what a chord is. These theorems we talked about in class many times, and we've done many problems. But just real quick, if the radius drawn to a chord is perpendicular, like in this case, right here, then we know it cuts that chord into two equal parts. So if that's 3, this is also 3. And then also here, this is just pretty basic. These are both diameters, which means they're just straight lines, so when they cross, they create congruent angles by vertical angles theorem. So you know that these two angles, 5x plus 10 and 5x plus 10 equal 12x minus 2. So you can set up an equation like that. Secants and tangents, this just introduced you to secants and tangents. Secants are lines that cross the circle exactly 2 times, while a tangent is a line in the plane of a circle that intersects the circle exactly 1 time. We also know that where it intersects the circle creates a right angle with the radius drawn to that point of tangency. That's very important. Another thing to note is that when you have 2 tangent lines like these that cross, then we know that these 2 segments are congruent. That's how we solve problems like this. We know that this is congruent to this is congruent to this, and this is congruent to this. Okay, and then that helps us solve problems. We also know, if we're trying to solve for a missing length like this, that since this is a right angle, we know that it's a right triangle, so we can use Pythagorean's theorem to solve. Let's call this B. You'd say 1.5 squared plus b squared equals 1.5 plus 1 squared. Okay. You then learned about inscribed angles. Inscribed angles are essentially just angles whose vertex is on the circle and whose endpoints are also on the circle, creating an intercepted arc. What's the relationship between that intersected arc and the inscribed angle? Well, the intercepted arc is 2 times the measure of that inscribed angle. So in this case, you'd have 2 times 44x minus 2. That would be the measure of G, let's do this in GF, FG, okay, arc FG, would be 2 times that measure. Okay. Angles related to the circles. So you have a few cases that are very much the same. That's these 3. You're going to do the same thing for all 3 of these. Okay, what you're going to do, we'll use this one because it's an easier example, is you'll take this arc, the bigger intercepted arc, and you will subtract the smaller arc. But we need to cut that in half for it to be equal to that angle. Okay, so in this case, 175 minus 57 would give us 118. Therefore, the measure of angle G is 1/2 of 118. So it should equal 59. So this is 59 degrees in here. It's going to be the same case for all of these. This is a tangent secant. This is a tangent tangent. So you can do this with this problem, the tangent tangent, but with the tangent tangent there's a quick shortcut. And all that is we know that the closest intercepted arc is supplementary to this angle here. So in this case it would be 60 degrees, since 120 plus 60 equals 180. Now the chord is a little bit different. Instead of subtracting like you do here, subtract, 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 we must add those intercepted arcs. So in this case, this angle in here for the chord, 124, is equal to 1/2 the sum of the intercepted arcs. So that's 197 plus 9x minus 3. Okay, so you'd have to solve that way. As for the angles created by tangent chord, like this, it's very much like inscribed angles. So the idea here is if you have an angle made from a chord and a tangent with the vertices on the circle, we know that the angle this creates is 1/2 the measure of the intercepted arc. So if this intercepted arc was, let's say, 100 degrees, we would know angle 1, this angle in here, this angle would be 50. In the case that, let's say, this angle right here, created by the tangent chord, were 140. We would know that BCA is 280 because it's 2 times that angle. So again, it's very much like the inscribed angles. So that was 4.5. We learned in 4.6 probably the most tough things you had to learn. Chord power theorem being one of them, especially if you have segments that were more than one term. For example, if you had x plus 2 for this segment and then you had x. If you had 10 right here and let's say 3. What we would do is we would multiply this segment, so that's x plus 2. We'd multiply that whole thing by this segment here, x. And we know that that is equal to 30. How did I get 30? Well, it's 3 times 10. That is the chord. You solve from there. Now, with the tangent secant power theorem, notice you'll have to square the tangent. Okay, you can see right here, you'll have to square the tangent. But with the secant, what you have to do is you need to take the external part. So here that's b, and you will have to multiply it by the entire secant. Okay, I think we have an example problem we can walk through real quick. Here's a tangent secant. So again, you'll have to take that tangent and you'll square it. And that is equal to the external part, remember that, the external part times the entire line segment. So that would be x plus 16. So in this case, you'd get 16 squared is equal to x times 2x plus 16, which would give us 16 squared is equal to 2x squared plus 16x. Here's another chord problem, but I wanted to show you guys that the secant is very much like the tangent secant. The only difference is you do what you do for the secant for both line segments. So for example here you'll do the external part times the entire secant, so that's 7 plus 9, and we know that that is equal to, again, the external part, 8x, times the entire secant, so that's 8x plus 6x. That's how you do the secant. I think that covers all of those, all these power theorems for segments. Arc length. You guys then learned about arc length. Arc length is essentially just taking the circumference of any circle, which is, let's say we went around here, we know that it is 2 pi times the radius. That's circumference. But when you're looking at arc length, you want to wonder, okay, well, given something like a radius of 36 feet, let's say, you know that the circumference is equal to, what is that, 72 pi. That's the entire circumference, but if you were just interested in finding, let's say in this case, GH, what you would do is you would take the amount of that circle compared to the whole thing, that's this ratio right here, and you would multiply it by the entire circumference. Now typically, you can do this in your head. You can say, oh, well, 140 over 360 reduces to 14/36, and this is still being multiplied by 72 pi. And you can reduce that more, can't you? We can divide the top and bottom by 2 at least. We get 7/18 times 72 pi. And this is about as reduced as you need to get it, so long as it says exact terms. Or if it says in terms of pi. Maybe the next step you could do is take 7 and multiply it by 72 and just keep that in the numerator. But this looks good to me. So that's arc length in a nutshell. Let's try this problem. Suppose you have a circle with a central angle of 34. So let's take a circle. And we know central angle is one whose vertex is in the center. Say this is 34 degrees. This is asking you, what does the subtended arc measure? You know that the measure of the arc is exactly the same as the central angle that makes it. So don't be confused by that. The next part of this question says, if the radius of the circle is 7 feet, what is the arc length? So that's where we plug in. We say, okay, well, we know the arc length is the degree of the arc measure over 360, and we multiply that by the entire circumference, which is 2 pi r. So in this case, we get 34 over 360. That at least divides by 2. I get 17 over 180. And then this is 14 pi. I could reduce this a little bit more. Let's see, I could divide 14 and the 180 by 2. I get 17 times 7 pi 90ths. And I think that's about as good as it gets. I'll get 17 times 7 is 70 plus 49, so 119 pi over 90. So that's the arc length. Not too bad, right? It's just the arc measure divided by 360 times the circumference. Alright, and now let's look at